In this video, we're going to work on problem 2.1.13 from the textbook. Given a sequence an of real numbers, define a new sequence bn by this formula. Bn is the average of a1, a2 up to an for n in n. In the first part, we have to prove that if the limit of an as n approaches infinity is a real number L, then the limit of bn as n approaches infinity is also L. And then in the second part, we have to find a counterexample to show that the converse does not hold in general. That means we can find a counterexample in which the limit of bn as n approaches infinity is L, but we cannot conclude that the limit of an as n approaches infinity is L. We call that a sequence an converges to a real number L if and only if for any epsilon greater than 0 there exists a natural number n naught such that the absolute value of an minus L is less than epsilon for all n greater than or equal to n naught. Note that this inequality is equivalently written as an is in between L minus epsilon and L plus epsilon for all n greater than or equal to n naught. In particular, the limit of an as n approaches infinity is 0 if and only if for any epsilon greater than 0 there exists some n naught in n such that this inequality is satisfied for all n greater than or equal to n naught. Note that over here we only need to replace L by 0. That's why it becomes this. Okay. Now we are ready to work on this problem. For any n in n, we have this. The absolute value of bn minus L is equal to the absolute value of a1 plus a2 plus so on plus an over n minus L. Okay, so this is the absolute value of a1 plus a2 plus so on plus an minus n times L over n. Okay, this is equal to the absolute value of a1 minus L plus a2 minus L plus so on plus an minus L, and everything is divided by n. Okay, now by the triangle inequality, this is less than or equal to the absolute value of a1 minus L plus the absolute value of a2 minus L plus so on plus the absolute value of an minus L, and everything is divided by n. Okay, now as you know, the limit of an as n approaches infinity is L. So we can continue by applying the definition of limit and prove that for any epsilon greater than 0, you can find an index such that starting from that index, the absolute value of bn minus L is less than epsilon. So I'm going to take any epsilon greater than 0. Okay. And now epsilon over 2 is also greater than 0. And now we can apply the definition of limit for this. So since the limit of an as n approaches infinity is equal to L, okay, there exists some positive integer n naught in n such that the absolute value of an minus L is less than epsilon over 2, and this is true for all n that are greater than or equal to n naught. So now from here we can have an upper estimate for the absolute value of bn minus L where n is greater than or equal to n naught. Now for any n that is greater than n naught, as you know, the absolute value of bn minus L is less than or equal to the absolute value of a1 minus L plus so on plus an naught minus L plus so on plus an minus L, okay, over n. Okay, so let me go ahead and use the summation notation for this. So this is equal to the sum of the absolute value of ai minus L, where I runs from 1 to n naught, and here this is the sum of the absolute value of ai minus L, where I runs from n naught plus 1 to n, and everything here is divided by n. Okay, so observe that there are n minus n naught terms in this sum, and each of the term here, as you know, is less than epsilon over 2. Okay, so the whole thing here is less than or equal to the sum of the absolute value of ai minus L, where I runs from 1 to n naught, plus n minus n naught times epsilon over 2. Okay, and everything here is divided by n. Okay, so I'm going to separate this into a sum of two terms. So this is equal to the sum of the absolute value of ai minus L, where I runs from 1 to n naught, over n, and here it is n minus n naught over n times epsilon over 2, so it can be written as 1 minus n naught over n times epsilon over 2. Okay, 1 minus n naught over n times epsilon over 2. Observe that this is less than 1. Okay, this is less than 1. Therefore, the whole thing is less than this sum, ai minus L, where I runs from 1 to n naught over n plus epsilon over 2. Now, for this sequence where n is greater than n naught, as you know, the limit as n approaches infinity is 0, so we can make it less than epsilon over 2 starting from some index. Therefore, the whole thing here is less than epsilon starting from that index. And by the definition of limit, Bn converges to L as n approaches infinity. So let me go ahead and continue with that idea. Since the limit of the sum of ai minus L, where I runs from 1 to n naught over n as n approaches infinity is 0, there exists an index n sub 1 that is greater than n naught. Here n sub 1 is also a natural number such that this sum ai minus L, where I runs from 1 to n naught over n, is less than epsilon over 2 and greater than minus epsilon over 2, but like this is always greater than or equal to 0, so we can omit that part, and in fact we only need this for all n that are greater than or equal to n1. Okay, now from here we're going to see that for any n that is greater than or equal to n1, we get this, and at the same time we get this upper estimate. Okay, so we see that the absolute value of Bn minus L is less than this sum over n plus epsilon over 2, and this sum is less than epsilon over 2, so the whole thing is less than epsilon. Okay, now to summarize, we take any epsilon greater than 0, and we already show that there exists an index n sub 1 such that for any n that is greater than or equal to n1, the absolute value of Bn minus L is less than epsilon. Therefore, by the definition of limit, okay, so the proof is complete. Now we're going to work on the second part of the problem. We have to find a counterexample to show that the converse does not hold in general. Okay, so we consider the sequence an given by an here is minus 1 to the nth for n in n. Okay. Then the limit of Bn, as n approaches infinity is the limit of the sum of ai, where I runs from 1 to n over n, and this is equal to the limit of the sum of minus 1 to the ith, where I runs from 1 to nth over n. Okay, so let's look at this sum from the top. So at first we have minus 1, and then we have minus 1 plus 1, and then we get minus 1 plus 1 plus minus 1, and so on. Okay, so this is minus 1, this is 0, and this is minus 1, and then you can show that the sum of ai where I runs from 1 to 4 is minus 1 plus 1, and then you add minus 1, and then you add 1. Okay, so and this is 0. So from here you will see that this sum is always greater than or equal to minus 1 and less than or equal to 0 for every n. Okay, you can easily show that. So by the squeeze theorem, this limit is 0. However, as you know, an is a divergent sequence. So an does not converge to 0 while bn converges to 0. So this is the counterexample for part B of the problem.